In Lecture 5, we're going to start taking a look at ionic compounds and how we name ionic compounds. A few announcements before we get started. Module 3, the pre-lecture reading will be due Thursday at 11:59 p.m. So that's reading the chapter that is due Thursday night. And then the recitation module will be due Friday night, the 11th. And Module 3, the post-lecture homework, that'll be due Sunday at midnight. I want to thank everyone who's taken the time to provide the feedback on the second week of class. Thank you for letting me know what's working, what's not working. I made that extra calendar based on some feedback, and I'm working on some extra practice problems as well. Those seem to be the two main things that people really were missing. So that master calendar I made based on your feedback, and I've made more practice problems in Chapter 1, Module 1, and I'm working on making some more practice problems for Module 2. I will be updating the grades for homework this week and the PlayPosit participation. So you should be working through that PlayPosit material on a weekly basis before completing the homework. So I'm going to update those grades this week, and so you will quickly find out if you've been doing the PlayPosit material or not. If you have not heard of PlayPosit, do not know what PlayPosit is, then yes, please email me, and we need to get on the same page because PlayPosit is how we're working through the lecture material. So a few review questions about calculating moles, determining moles, right? From Thursday's material, 1 mole equals Avogadro's number of atoms or molecules, 6.02 times 10 to the 23. And we can go directly to the periodic table and convert the weights that we see on the periodic table in AMU, atomic mass units. We can convert that directly to grams, and that'll provide us the information of how many grams of that element you would need to have 1 mole of that sample. So for example, if we went to the periodic table and looked up calcium, calcium is approximately 40.078 atomic mass units. That means I would need approximately 40.078 grams of calcium to have 1 mole of elemental calcium. Aluminum, I could look up aluminum. Let's see, aluminum is over here. Aluminum is, as we can see, 26.981538 AMU. That means I would need to have approximately 26.98 grams of aluminum to have 1 mole of aluminum. 6.02 times 10 to the 23 atoms of aluminum. The amount of calcium needed is different than the amount of aluminum needed because their mass from the periodic table is different. But what's constant is the number of atoms in that sample. And the same works for molecular mass. So if I have sodium chloride, for example, I would look up the mass of sodium as 22.98 AMU. The mass of chlorine is 35.45 AMU. Add those two together, and I would get 58.44 AMU for sodium chloride, which means I would need to have 58.44 grams of sodium chloride to have 1 mole. So that 1 mole would contain 6.02 times 10 to the 23 molecules of sodium chloride. So here are a few sample calculations. Calcium. Calcium makes up a large portion of the human body, mostly in our teeth and our bones. The average human body contains approximately 1.02 kilograms of calcium. And we're asked, how many moles of calcium does that represent? Well, from the previous slide, we went and looked up the atomic weight of calcium as 40.078 AMU, which means I need 40.078 grams for 1 mole of calcium. So now I need, my conversion factor is grams per mole, but I have a mass of kilograms. So I need to convert that to grams. Well, I know 1 kilogram is 1,000 grams. So multiply by 1,000, and I get approximately 1,020 grams of calcium. 1,020 grams of calcium. I know for every 1 mole, because I want to find out moles, right? I need the conversion factor, allows me to go from grams to moles. For every 1 mole of calcium, I would need 40.078 grams of calcium. Grams of calcium cancel out, and I'd be left with moles of calcium. So divide 1,020 by 40.07, and I get 25.45 moles of calcium. Got 3 significant figures here, so to report this to the correct number of significant figures in scientific notation, right, this would become 2.55 e to the 1 moles of calcium. I would move this decimal place over 1, and I'm going to drop everything after the 4. So 5, right, is greater than or equal to 5, so I'm going to round up 4 to 2.55 e to the 1 moles of calcium. Here's another good review question. There are approximately 75 milligrams of caffeine, which is CHE-106-L-Recture-5-PART-1-2020 in an espresso shot. If you have a triple shot of espresso in your coffee, how many moles of caffeine does that represent? So if we have 3 75 milligram shots of espresso added to our coffee, right, we've got 3 times 75 milligrams, or 225 milligrams of caffeine. Well, we have a little bit more work to do here because you need to know the molecular weight of caffeine. So to break this down, our caffeine is C8H10N4O2, which means I have 8 carbons, I have 10 hydrogens, 4 nitrogens, and 2 oxygens. I'd go to the periodic table to see that carbon was 12.0107 AMU, hydrogen is 1.00794 AMU, nitrogen is 14.0067 AMU, oxygen is 15.994 AMU. So multiply 8 by 12, 10 by 1, 4 by 14 to determine that I've got approximately 96.0856 AMU of carbon, approximately 10.0794 AMU of hydrogen, 56.0268 AMU of nitrogen, and 31.9988 AMU of oxygen. So to determine the molecular weight, right, so I can determine the molar mass, I add those all together to see that caffeine is approximately 194.906 AMU. So that means I would need to have 194.1906 grams of caffeine to have 1 mole of caffeine. So my information is in grams per mole, my mass is in milligrams. I need to convert that from milligrams, so I know that there's 1,000 milligrams are in 1 gram. So I have 0.225 grams of caffeine, and I know that for every 1 mole of caffeine, I would need approximately 194.1906 grams of caffeine. So grams cancels out, and I would have approximately 0.00115865 moles of caffeine. Now thinking about that with significant figures, my significant figures from this calculation would be my weight. My total weight, I would say 225 milligrams. So to report this to 3 significant figures based on the 225 milligrams, be 0.00116. We're going to drop everything after the 5. Because that number is greater than 5, we're going to round the 5 up to 6. Moving that into scientific notation, I want to move this decimal place 1, 2, 3 places to the right. So 1.16 e to the negative 3 moles of caffeine. So what made this problem different and a little bit more work was that I did not give you the molecular weight, right, of that compound, the molar mass of that compound. You had to find that by using the information given on the periodic table of the elements. So for the next question, we're asked how many molecules of caffeine does that represent? So the previous slide, we determined moles of caffeine. I determined that I had 1.16 e to the negative 3 moles of caffeine. And I want to find out, I'm going to multiply that something that gives me molecules of caffeine. The only thing that relates moles and molecules is Avogadro's number. I know for every 1 mole of a sample, I need to have 6.02 e to the 23 molecules in 1 mole of caffeine. So moles of caffeine cancel out. I multiply 1.16 e to the negative 3 by 6.02 e to the 23 to determine that I have approximately 6.98 e to the 20 molecules of caffeine. So what you should be very familiar with, and these are the steps that we're working with here, if I give you grams of a sample, right, how to convert that to moles. We would need either the atomic weight, if it was an element, or the molecular weight if it was a molecule. Once I have moles, to determine, right, atoms, the number of atoms or molecules, I want to use Avogadro's number. And then if I want to go one step further, and that's what we're going to do on the next slide, if I need to determine how many atoms are within a molecule, then I would need to use the coefficients from the formula. The chemical formula. And we'll do that calculation on the next slide. But for this one, 6.98 e to the 20 molecules of caffeine. All right, so for the last question, here's that last question. Same preface, we have 225 milligrams of caffeine, we found moles, we found molecules. Now we're asked to find how many atoms of nitrogen would be within that sample. So on the previous slide, we determined that there are 6.98 e to the 20 molecules of caffeine. And if we were to look at a molecule of caffeine, CH10N4O2, and break that down, we would see that I have, right, 8 times as much carbon, 10 times as much hydrogen, 4 times as much nitrogen, and 2 times as much oxygen, just using those subscripts that are provided in the formula. It's telling me I have 8 carbon, 10 hydrogen, 4 nitrogen, and 2 oxygen. So to finish this calculation, right, I need to multiply by something that turns molecules of caffeine into atoms of nitrogen. Well, I'm going to use the formula. I'm going to use the formula, the formula of the molecule, because that tells me in 1 molecule of caffeine, I have 4 atoms of nitrogen. So that's my conversion factor. So that means I have to multiply 6.98 e to the 20 by 4. Molecules of caffeine cancel out. I multiply that by 4, and my final answer should be approximately 2.79 e to the 21 atoms of nitrogen would be in that sample. So for that last step, we had to use the information provided in that formula to tell us, once I know how many of those molecules I have, I can then break that down to figure out, okay, within that sample, how many atoms of carbon are there? How many atoms of hydrogen or nitrogen or oxygen, simply by using the subscripts provided in that molecular formula.